All right, good morning again, guys. For today, we'll continue on our venture into the third unit of the course, which again is talking about limits. But this is a different flavor or a different take to the classical notion of limits na nakita nyo sa elementary calculus. Kasi ngayon, equipped na tayo ng mas maraming kaalaman about the real number system and a list or an ordered list of real numbers, which we call sequences. All right. Then, ang ginagawa natin, we are capitalizing on that notion para i-build up yung limits, which is one of the pillars of modern day calculus. All right? Kasi kung matatandaan nyo, yung pagkaka-define ng derivatives, limits lamang yon ng difference quotients. Tapos yung integral, limit lamang siya ng Riemann sum. So those big guys in calculus are all reliant on this tiny concept we call limits of a function. All right? And malaki yung relationship between limits of sequences sa limits of functions. Kaya kung makikita nyo sa development natin ngayon or in today's lecture, I will weave those two concepts together para makita nyo na yung konsepto ng limits ng isang function over an arbitrary set is basically sort of an extension or generalization of the notion of limits of sequences. Kasi yung sequences, functions din yan. Kaya lang ang domain niya ay set of natural numbers. So ano yung nangyayari or paano natin i-define yung konsepto ng limits o ng parang convergence, air quotes, ng isang function kapag kayong domain niya ay hindi na lamang natural numbers. And since its domain is usually a subset of R, which we know to be a complete ordered field, pwede nating tingnan ngayon yung behavior ng isang function habang palapit ka ng palapit sa isang limit point ng kanyang domain. Hindi na tayo malilimitahan dun sa pagtingin dun sa ano yung nangyayari kapag kayong subscript ay lumalaki without bounds, katulad ng ginawa natin sa sequences. Now we can analyze a function with an arbitrary domain in a more localized fashion. So pwede nating makita ano yung nangyayari dun sa mga function values habang yung mga excess na pina-plug in natin dun sa function ay palapit ng palapit dun sa isang limit point nung domain. Right? And as a result of that, we look at this more generic definition for the limit of a function, which again has a very subtle but yet a very profound difference from your Math 36 definition. Kasi rito, hindi natin nire-require na yung function ay maging defined sa isang open interval containing the number at which you are evaluating the limit at. All we require is that the number at which we evaluate the limit, say at the number C, should be a limit point of A. So ang usapan, dapat nagkukumpul-kumpulan yung mga elements ng domain around a neighborhood of the number C. Okay? And we say na yung limit ng function as x approaches c ay equal kay L kapag ka gusto mong yung mga function values ay maging malapit dun sa number na L, then all you got to do is to guarantee that the x's are sufficiently close to the number c. All right? So that means in more mathematical terms, if I issue a challenge epsilon greater than 0, you should give me back a delta greater than 0, such that whenever the distance between x minus c is less than delta, then it will follow that the function value is within epsilon units away from L. And last time we revisited how to use this definition in order to prove limit statements na ginawa nyo na sa Math 36 na siguro nun mechanical nyo lang ginawa kasi ako ganun yung nangyari sa akin. Ginagaya ko lang talaga yung pattern na binigay ng teacher ko dun sa proof. But hopefully now, with your maturity, mathematically speaking, and yung mga examples natin last time, medyo na-appreciate natin yung pag-prove ng limit ng isang function, right? And then I think we ended up the discussion last time by looking at ano yung isang illustration ng profound difference between the preamble of definition 3.1 and your Math 36 definition. Kaya sabi natin, noon ang kino-conclude natin ay ang limit ng square root of x as x approaches 0 does not exist. This is Math 36. Kasi um, hindi to papasok dun sa definition ng Math36 kasi walang open interval around 0 for which the square root function will be defined at every number. Okay? So tapos ang magiging basihan natin ay yung two-handed limits. So yung or yung one-sided limits. Yung limit from the left, limit from the right, dahil wala tong limit coming from the left of 0, then we were forced to conclude that the limit doesn't exist. Now, under our math 155 definition, which is exactly what we have on screen right now, we can say na, hold on, hindi natin i-discount yung pagkakaroon ng limit ng square root of x just because there are no numbers to the left of 0 for which the function is defined. Ang domain nito ay set of all non-negative real numbers, pero nag-accumulate yung mga elements ng domain around 0. Yun nga lang, mula sa kanan ni 0. But the definition doesn't require na kailangan accumulation points siya coming from the left and coming from the right. So with everything in here, I think we also proved last time na ang limit talaga nito ay equal kay 0. Okay? Kasi nasa-satisfy niya lahat ng ingredients o lahat ng requirements ng definition, including this more generic preamble. Right? Okay, so now we will go to, as promised, go over what is the relationship between limits of functions and limit of sequences, right? And theorem 3.1 gives us sort of a characterization of the limit of a function with an arbitrary domain vis-a-vis yung limit ng isang sequence, all right? And this is very important because in our limit proofs, we will often rely on theorem 3.1 rather than going through definition 3.1. Kasi katulad sa Math 36, halimbawa, para ma-prove na kung ang limit ni f ay equal ka ng limit ng f of x plus g of x as x approaches c ay equal sa limit ni f plus limit ni g, we always went back to the definition, the epsilon delta definition. Pero dito, with the beauty of our development in Math 155 is that we can avoid that ruckus of going through that epsilon delta thing sa pagpo-prove ng mga limit theorems kasi meron na tayong mga established theorems about limits of sequences. And theorem 3.1 will provide us a way on how to capitalize on that knowledge para ma-prove yung mga limit theorems kapag yung domain ng function ay hindi na lang basta set n, right? So let's see what theorem 3.1 says. Actually, I said it's a characterization, so it's an equivalent statement, all right? So let's see. So it says, given a function f whose domain is a subset of r towards a set of real numbers, and again, a limit point x sub 0 of a, then the following two statements are equivalent. Una, yung limit ni f of x as x approaches x sub 0 ay equal kay L. Tapos yung pangalawang statement, sa kahit na anong sequence properly contained in A na never naging x sub 0 yung nth term. So yun yung only condition. Kahit na anong, pag kumuha ka ng kahit na anong sequence na ang terms ay galing kay A minus the set containing x sub 0, all right? Such that that sequence converges to x sub 0, it follows that the limit of f of xn as x approaches infinity ay equal kay L. So, but before going further, let's, ano sa English ang himay-himayin? Let's himay-himayin, so konyo, no? So, tingnan natin ano yung mga sinasabi nitong definition, nung second statement, because medyo maraming nangyayari. So, ibig sabihin dito, kumuha ka raw, kapag kumuha ka ng kahit na anong sequence doon sa loob ni A, pero bawal si x sub 0 maging term doon sa sequence mo, such that yung sequence na kinuha mo ay convergent at nagko-converge siya kay x sub 0, then magpa-follow daw, or dapat mag-follow, na yung limit ng f of xn as n approaches infinity ay equal kay L. So I hope this is clearly a limit of a sequence. So if you will compare this limit statement with this limit statement, magkamukha sila except that this is the limit of a generic function, Pero ito ay limit ng sequence. Alright? Anong sequence yung kinunan ko ng limit dun sa statement number 2? Ang kinunan ko ng sequence ay yung sequence ng mga function values. Alright? Pwede kong imagine, alright, meron akong dalawang sequence sa statement number 2. Sequence ng mga xn's, alright, tapos sequence ng mga f of xn's. So meron ako ditong sequence ng f of x1, f of x2, f of x3, and so on. Right? Tapos, pag kinuha ko daw yung sequence na to, pag kinuha ko yung limit ng sequence nitong mga function values, equal daw yon kay L. And basically, this is the relation between the limit of a function and the limit of a sequence. Right? Ang limit ng isang function as x approaches x sub 0 ay equal kay L. If and only if, kasi equivalent daw, sabi ng theorem, yung statement 1 at saka statement 2. If and only if, pagka kumuha ka ng kahit anong sequence doon sa loob ng domain, mapera lamang na yung x sub 0 dapat hindi term doon sa sequence, such that yung sequence na yun ay nagko-converge. So in other words, if you take any convergent sequence coming from the domain that specifically converges to x sub 0, then yung limit ng sequence ng mga function values ay equal kay L. Right? And it's a biconditional statement. So kung mas madali para sa inyo na mag-compute ng limit ng isang function, then that's fine. Then sure ka, pagka alam mo yung limit ng function ay equal kay L, sure ka na kapag kumuha ka ng sequence ng mga x values na nagko-converge kay x sub 0, yung sequence of function values will converge to the number L. Right? And the converse is also true. Ano yung converse? Kapag kumuha ka ng kahit anong sequence dun sa domain na nagko-converge kay x sub 0, kunin mo lamang daw yung function value nung yung sequence ng mga function values, evaluate mo yung limit ng sequence na yon, pag convergent yung sequence na yon, then sure ka na yung limit ni f as x approaches x sub 0 ay equal rin kay L. Right? So parang ito yung pabaligtad ng Hitching theorem na natutunan niyo sa Math 38. Di ba sa Math 38, pagkukuha daw tayo ng limit ng isang sequence. Ito yung terms ng sequence ko. Okay. Tapos gusto kong makita yung limit ng sequence na to dahil wala tayong masyadong algebraic theorems. Tapos hindi tayo makakagamit ng L'Hopital's rule, hindi tayo makakagamit ng mga kung ano-anong techniques para ma-evaluate ang limit ng isang sequence. Alright? Ang ginagawa natin, gumagamit tayo ng Hitching theorem. Yung Hitching theorem, nakikisakay yung limit ng sequence doon sa limit ng function. Kasi masanay tayo na mag-compute ng limit ng mga functions o mga continuous functions. So ang ginagawa natin dati, pag-evaluate ng ng limit ng mga komplikadong sequences, kinukuha natin yung extension nung sequence to allow its domain to be the set of real numbers or a subset thereof. Tapos yung continuous function version nung sequence, yun yung kinukuhanan natin ng limit. And this is basically statement number 1 implying statement number 2. Kasi alam natin yung limit nung continuous function f ay equal kay L. Sure tayo na pag kumuha tayo ng kahit anong sequence ng mga function values, then yon ay magko-converge dun sa same limit. Okay. Ang madadagdag sa ating mga kaalaman today ay yung pabaligtad. Kasi yun pala, pwede mong gamitin yung Hitching theorem ng pabaligtad. Kung given ka ng isang function, kukunin mo yung limit niya as x approaches x sub 0, pwedeng tumingin ka na lamang sa isang sequence ng mga function values. Pag nakuha mo yung sequence ng mga function values na yon, tingnan mo kung convergent. Pag nag-converge siya sa isang number L, then yung number L na yon surely is also the limit of the continuous function or your function with a domain that is not the set of natural numbers. Okay? Now, let's try to write a proof for this. But I hope this makes sense. The statement makes sense. And you will see the utility of this. Kasi if we will be able to prove this, then yung mga limit theorems about functions with a generic domain ay kaya nating ma-prove using Theorem 3.1 plus yung mga theorems na natutunan natin from unit number 2. All right? Okay, let's see the proof. Now, this is a biconditional statement kasi sabi equivalent to statement 1 saka si statement 2. So let's start with the forward implication, meaning statement 1 is that x approaches the limit point x sub 0 I equal KL, right? And we want to show, okay, using that, we want to show that for every sequence, for any sequence x sub n, which is a subset of the domain set minus set containing x sub 0, right? With xn approaching x sub 0, we have limit of f of x n as n approaches positive infinity ay equal kay L. So ang assumption natin, alam natin na yung limit ng function ay equal kay L. Ang gusto nating ipakita ay pag kumuha tayo ng kahit na anong sequence doon sa set A less containing x sub 0 that converges to x sub 0, then the limit of the sequence of the function values ay equal kay L. Alright? So, yun yung gusto nating ipakita. Pero ano lang yung pwede nating gamitin? Pwede lang nating gamitin na yung limit ni f of x as x approaches x sub 0 ay equal kay L. So what we know from the assumption is that given any epsilon greater than 0, okay, we know that there exists a delta greater than 0 such that whenever the absolute value of x minus x sub 0 is between 0 and delta, then we are sure that the absolute value of f of x minus L is less than epsilon. Okay, so yan yung sinasabi nung pagiging limit ni L ni f of x. Alright? Gusto nating ipakita ngayon, kumuha ako ng kahit anong sequence na nagko-converge kay x sub 0, yung limit ng mga function values nung terms ng sequence ay nagko-converge din kay L. I'm gonna do that. So I'll consider a sequence xn coming from sorry, naputol yata ako doon. So, yeah, kukuha ko ng isang sequence mula sa set na to such that xn converges to x sub 0, okay? And I want to show that the limit of the function values is equal to L, all right? Now, since the sequence xn is convergent, okay? Kasi yun pa lang yung uli yung meron ako, right? Alam ko lang meron akong sequence, nandito siya sa set na to, tapos nagko-converge siya kay x sub 0. Gamitin ko kaya yung definition ng convergence noong mga xn's papunta kay x sub 0. And then I'll use a special trick for it. Explain ko mamaya kung bakit ito yung kailangan kong gamitin. So dahil si xn ay convergent, then for the same delta as above, okay, kasi meron akong delta. Well, bakit alam ko na si delta? Kasi di ba dun sa convergence, alam natin definition ng convergent ng isang sequence for any epsilon greater than 0, there exists a starting index capital N, blah, 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 blah. All right? Ngayon, makikita nyo, ang gagamitin kong epsilon dun sa definition ng convergence ng sequence ay si delta. Bakit yun yung gagamitin ko? Kasi dun sa definition ng limit ng isang function, si delta ay laging nakakabit dun sa distance ng mga x values mula dun sa accumulation point. Right? Tapos si epsilon, siya naman yung distance mula dun sa function value at dun sa purported limit. Okay? Kaya alam ko, most likely, kapag ka nagdi-deal ako with x's, laging ang nakakabit dapat sa kanya na distance ay delta. Alright? Pag function values yung pinaglalaroan ko, dapat ang nakadikit sa kanya na distance ay epsilon. Alright? And since I am using, or I'm trying to use values to the accumulation point, then at the back of my mind or my instinct tells me, yung delta ang gagamitin ko rito. So papalitan ko yung epsilon dun sa definition ng convergent sequences ng delta. In other words, for any delta greater than 0, we can find a starting index, blah, blah, blah. Right? Yun yung isusulat kong susunod. Pero ang kagandahan dito, meron na akong delta. Yung delta rito ay nagaguarantee na kapag nasa-satisfy ng excess, etong inequality na to, then yung function values will satisfy the epsilon inequality. All right? That's why it pays to use the same delta over here as the challenge doon sa paghahanap ng starting index, capital N. Okay? So to continue this sentence, I can say that since xn is convergent, then for the same delta as above, there exists a starting index capital N such that for all little n greater than or equal to capital N, we have absolute value of xn minus x sub 0 is less than delta. All right? So basically, I hope this rings some bells. So sana hindi dahil 2 weeks tayo nakabakasyon, nakalimutan nyo na yung convergence ng sequence, right? So ito yung basically definition ng convergence sequence, but epsilon was replaced by delta, right? And then look at this now. Alam ko na yung mga pinag-uusapan nating xn, yung mga x sub little n of interest to us are within delta units away from x sub 0. And this delta is the same delta that we have from the limit statement, all right? From the limit statement about little f as a function, all right? So ibig sabihin, etong delta na to ay kaparehas ng delta na to, pero nasatisfy ni x sub n, etong inequality na to. So therefore, ang sabi ng definition ng limit, kapag ka nasatisfy yung delta inequality, magfa-follow yung epsilon inequality. So since this is the same delta as the one above, then I can say na yung function value ni x sub n ay laging within epsilon units away from capital L, right? Kasi kung ano yung x na nakasatisfy ng delta inequality, pag pinasok mo yun sa loob ni f, all right? Tapos nag-minus ka ng L, yung absolute value na yon mas maliit sa epsilon. And that's exactly what I did here. I use xn as the input to little f, all right? Minus L, take the absolute value. By this statement, that will be less than epsilon. Okay? And let's, again, summarize what we have so far. So here we're given an arbitrary epsilon greater than 0, all right? We were able to find a starting index capital N such that for all indices after capital N, the absolute value of f of xn minus L is less than epsilon, which is precisely what the definition of the limit of a sequence is. So from here, we can say na, all right, f of xn converges to L by definition ng convergence ng isang sequence, right? So essentially, we have established what we want in this part of the proof, okay? So is that clear, guys? Any questions? Okay, kung wala namang questions, kumpletuhin natin yung proof. Remember, it's a biconditional statement, so meron pa yung converse. Kailangan nating i-prove yung converse, which tells us that we will assume here that for any sequence inside the domain less the set containing x sub 0 that converges to x sub 0, we have f of xn converging to L, right? So ito yung assumption natin. Ipagpalagay natin na kapag ka meron akong sequence ng mga x's na nagko-converge kay x sub 0, sure tayo yung sequence ng mga function values ay nagko-converge kay L. What we want to show is that the limit of f of x as x approaches x sub 0 ay equal kay L. All right? But the first question that we need to ask is this assumption enough, okay, to talk about the limit of a function f, right? So kasi merong preamble, yung definition ng limit, which is often neglected or often ignored. Alright, so kailangan nating i-check. Define lamang yung function kapag yung number na kung saan kinukuha mo yung limit ay isang limit point. Alright? But we are sure that it is a limit point kasi actually hindi na pala kailangang itanong yan. Sorry guys. Nasa ano nga pala siya? Nandun siya sa premise ng theorem. Kasama siya sa premise ng theorem. So, okay, covered na pala yung part na yon. Sure tayo na si x of 0 ay limit point, so it makes sense to talk about this limit. Okay, now paano ko to iprove? I'll use a proof by contradiction. So I will do this by contradiction. Okay, so I'll suppose for the sake of contradiction that the limit of f of x as x approaches x of 0 is not equal to L. Okay, kunwari lang na mali yung theorem o mali itong converse. So, nag-hold si assumption pero yung limit ng function ay hindi equal kay L. Right? Tapos dito natin kailangan yung kagalingan nyo mula sa Math 101 na pag-negate ng definition. Alright? Kasi ang daming nangyari dun sa definition ng limit. Alright? Pero ngayon, marami kasing quantifiers na involved. Now, we want to get the negation of the definition kasi ang assumption natin dito in our proof by contradiction is that the limit is not equal to L. Alright? So, I hope tandapan nyo kung paano mag-negate ng isang statement o isang proposition involving quantifiers. Okay? Tanda ko to, pinagawa ko to kila Prince at saka Trisha last semester. So, tatawagin ko sana sila pero baka hindi na sila umattend next time. So, yeah, i-ano natin siya, i-negate natin. So, for all epsilon, so ibig sabihin there exists an epsilon, okay, greater than 0, such that ang nasa definition, there exists a delta. Alright? So, ngayon, i-negate ko yung there exists a delta. So, magiging for all delta greater than 0 na siya. Alright? Negation ng there exists ay for all. Negation ng for all ay there exists. Alright? Such that for all delta greater than 0, and x's with x minus x of 0 between 0 and the delta, we have the following. We have f of x minus L is greater than or equal to epsilon. So yan yung negation ng definition. Yung there exists, yung for all epsilon, naging there exists an epsilon. Yung there exists a delta, naging for all delta. Alright? Tapos, di ba meron kang absolute value implies, delta inequality implies epsilon inequality. Now, pag nag-negate ka ng isang implication, nagiging false lang ang isang implication kapag true implying false. So yung premise, dapat totoo pa rin yung premise nung implication dun sa definition. So totoo pa rin, hindi ko babaguhin yung delta inequality, pero ininegate ko yung epsilon inequality. Alright? So ibig sabihin, merong isang epsilon na sa kahit ano pang delta na piliin natin, such that x is within delta units away from x of 0, we have this inequality. Alright? So ito yung gusto kong i-contradict. Right? Now, we will consider, let's see. All right, let's have this. Okay, I let, for each, paano ko ba sasabihin? Ang idea kasi ay bubuo ako ng isang sequence. Kasi gusto kong magamit itong assumption. Ang gagawin ko ay bubuo ako ng isang sequence ng mga x's na magko-converge kay x of 0. Tapos, pagka nakabuo na ako ng ganung sequence, di magpa-follow na yung limit ni f of xn ay equal kay L. Papakita ko na hindi siya magko-converge kay L kung tatanggapin natin yung supposition na ang limit ni f ay hindi equal kay L. So yun yung idea. Bubuo ako ng isang sequence ng mga x's na magko-converge kay x sub 0. Right? So in particular, I mean, this is telling us that for all delta greater than 0. So that means I can choose any delta. So that means in particular, for delta equals 1 over n, for any natural number little n, okay, we can find an x element of A that is outside of x sub 0, or that is not equal to x sub 0, such that ang x minus x sub 0 ay less than 1 over n units away mula kay x sub 0. All right? So, bakit okay. Bakit ako sure na meron akong mga xn na makukuha, right? So, sabi rito ay let's see, paano ko ito i-phrase ng maayos? Alright, so ang assumption kasi natin, si x sub 0 ay isang limit point. Alright, so dapat siguro yun yung ginamit ko. Yeah, mag-insert ako dito ng isang statement. Lagay natin na, okay. Since x sub 0 is a limit point of A, mukhang ito pala yung tamang reason kung bakit kaya ko itong isulat, right? So dahil by the premise of theorem 3.1, we know that x sub 0 is a limit point of A. Then for any, dahil limit point yan, pwede akong pumili ng kahit anong epsilon neighborhood around x sub 0 na magko-contain ng mga elements ni A other than x sub 0, right? Kasi nga, nagkukumpul-kumpulan yung mga elements ni A around x sub 0. So pag pumili ako ng kahit anong epsilon neighborhood, specifically, I'll choose 1 over n to be that epsilon, okay? Or that delta, okay? Kasi nga sabi ko, delta na yung lagi kong ina-associate sa mga x's. So pagka kumuha ako ng 1 over n neighborhood around x sub 0, lagi akong may mahanap na element ni A different from x sub 0 that belongs to that epsilon neighborhood. And I'll call that element x sub n. All right? So that means this is true, right? Pagiging limit point lamang ni x sub 0 kay A. Kahit ano pa si 1 over n, where n is any natural number, I can always find an x sub n that belongs to the neighborhood. Tapos pag kinolekta ko yung mga x sub n's na yon as a sequence, I know that x sub n will converge to x sub 0. Sorry, naputuloy ako. I think this is the theorem before Heine-Borel. All right? Kapag siya ay limit point, may makikita tayong isang sequence na nagko-converge kay limit point. All right? So yun yung ginamit ko rito. But essentially, what we have seen here, actually, pwede ko na palang idiretso. Okay? Itong inequality na to ay nag-hold, tapos ito yung pinili ko na delta. So ibig sabihin, sorry, under this epsilon, all right? Dahil nag-hold itong statement na to sa lahat ng mga delta, it will hold for delta equals 1 over n. Tapos, ibig sabihin, mag-hold itong premise na to. Dahil nag-hold itong premise na to kay x sub n, ibig sabihin magpa-follow itong inequality involving epsilon. All right? So that means this will imply that the absolute value of f of xn minus L is greater than or equal to epsilon. All right? So that means dahil ito ay totoo, it will imply that f of xn will not converge to L. Right? Kasi lagi tayong may makikitang x sub n na ang function value ay may distance kay L na mas malaki kesa sa isang given epsilon, which is the same epsilon we used in the first, the same epsilon we claim to exist here. At dahil, but this thing or this statement will contradict our assumption. Kasi sabi natin sa assumption, kahit ano daw sequence ng mga x's na nagko-converge kay x sub 0, magpa-follow na yung sequence ng mga function values. But here we have a result claiming that we have the sequence of function values to be not converging to L. Okay? So since my contradiction, therefore, hindi tayo pwedeng pumayag ng limit ng f of x as x approaches x sub 0 ay hindi equal kay L. So kailangan equal siya talaga kay L. And that completes our proof. Okay? So with this theorem, meron na tayong isang napakalapit na relationship between limit of sequence and limit of a sequence and limit of a function. Okay? And ang dahilan kung bakit sila ay or ano yung main ingredient kung bakit nagkaroon ng magandang relationship between the two is the assumption that the number of interest x sub 0 is a limit point of the domain. Okay? Kasi kung limit point lang siya, yun lang tayo, dapat maging limit point si x sub 0 para sure tayo na merong sequence dun sa domain na magko-converge kay x sub 0 because that's very crucial in statement number 2. Okay? So any questions so far? I hope everything is still clear. Everything is making sense. Okay, now let's see how we can take advantage of theorem 3.1 together with the statements we have for limits of sequences insofar as proving limit theorems are concerned. Okay, tingnan natin yung unang result, which is corollary 3.1. Ang sabi niya, pag meron tayong function ng domain ay A, tapos kumuha tayo ng isang x sub 0 na limit point ng domain, and if f has a limit, then this limit must be unique. All right, this is basically, or this is I think the first theorem that you met in Math 36 with regards to limit. So ang proof natin nun ay contradiction din, pero gumamit kayo ng epsilon delta. All right, nagbigay kayo ng epsilon, tapos nakakita kayo ng delta 1 at saka delta 2 that mag-hold yung inequalities para dun sa limit ay equal kay L, tapos yung limit ay para kay M. Thus, eventually, you'll be able to show that L is equal to M. So that's one way to prove it, but we can prove it taking advantage of theorem 3.1 and the uniqueness of the limit of a sequence. Okay? So tingnan natin paano sinulat yung proof. I think, tama. Ang ginawa ni lecture notes, consider niya, sinulat niya yung proof by contradiction. How was it done? So assume mo na hindi unique yung limit. Kunwari may dalawang limit si f as x approaches x sub 0. So suppose the limit the limit is equal to two numbers, L1 and L2, two different numbers, L1 and L2. Tapos by theorem 3.1, okay, ibig sabihin merong sequence. Kaya may sequence dun sa domain na nagko-converge kay x sub 0, pero yung sequence of function values ay nagko-converge kay L1, tapos nagko-converge din kay L2. Alright? So, actually, mali pala. Dapat isa lang yung sequence. So, dahil sinabi natin yung limit ni f of x as x approaches x sub 0 ay equal kay L1 and also equal to L2, okay? Ibig sabihin, by theorem 3.1, meron tayong makikitang sequence na nandun kay domain na nagko-converge kay x sub 0, tapos yung function values ay nagko-converge din parehas kay L1 at saka kay L2. But this is a contradiction because we know that the limit of a sequence, if it exists, will be unique. All right? So ibig sabihin, hindi pwedeng magkaiba yung limit ng parehas na sequence na f of xn. Because kasi parehas dito yung parehas yung sequence xn, kinuha ko lang yung limit ng mga function values. So these two sequences of function values are exactly the same. Tapos sabi ng theorem 3.1, kasi limit ng f ay equal kay L1, so dapat ito ay magko-converge kay L1. Pero inassume natin dun sa proof na equal din yun kay L2. So ibig sabihin by theorem 3.1, yung sequence of function values dapat magko-converge din kay L2. But that will contradict the fact that the limit of a sequence is unique. So kaya mafo-force tayo to say na, oo nga, parang may inherit ng limit ng isang function ang uniqueness ng limit ng isang sequence. Right? So, and I think this is much easier than the proof that you used in math 36 na nag-epsilon greater than 0 kayo, tas meron kayong delta 1 saka delta 2. And this is much more efficient. Kaya lang, ang dahilan kung bakit mas maiksi yung proof natin, ang dami na natin pinagdaanan before. Alright? Natutunan na natin yung theorem 3.1, tapos na-prove na rin natin before na unique ang limit ng isang sequence. Okay. Now, let's look at another result. Kaya ang tawag sa mga theorems na to ay corollaries kasi nagpa-follow sila directly from theorem 3.1 and a bunch of theorems from unit number 2. So basically, yung corollary 3.2, ito yung mga algebraic limit theorems para sa functional limits. So which is basically kamukhang kumaka nung nakita natin mula dun sa limit ng sequences. All right? But basically, this tells us that if the limit of a scalar multiple of a function is the same scalar multiple of the limit of the function. The limit of a sum is the sum of the limits. The limit of a product is the product of the limits. And the limit of a quotient is the quotient of the limits, provided, of course, that g of x is non-zero and the limit of g is not equal to 0. Okay? Tapos tingnan natin, paano natin ito iprove? Again, gagamitin ko yung theorem 3.1 at yung corresponding results mula sa unit 2. Okay. Now, pili tayo ng isa. Anong gusto niyong gawin? Actually, magkakasing level lang naman tong apat na to. Probably I'll choose to prove part 1 and then you can try to prove the other 3. Okay, so let's prove part 1. Okay, so ang assumption dito, ang limit ni f of x ay equal kay L as x approaches x of 0. So here I can say that by theorem 3.1, okay, tama ba yung phrase ko? Gagamitin ko na kagad si theorem 3.1. So ibig sabihin for any sequence ng xn coming from the domain less the limit point with convergence to x sub 0, we have the following. We know that the sequence of function values will converge to L. Galing dito sa assumption ng limit ni f as x approaches x sub 0 ay equal kay L. I-apply ko si theorem 3.1. Kapag ang limit ng function ay L, ang limit ng sequence ng kahit anong function values, ng kahit anong sequence of function values wherein the inputs are coming from a sequence that converges to x sub 0, ay magko-converge din dun sa kaparehas na limit. Okay? But this will imply that the sequence k times f of xn will converge to kl by our algebraic limit theorems for sequences. So, pakisulat na lang ng buo. So, alam na natin to mula sa theorem, mula sa unit 2, na kapag ka nag-multiply ka ng isang constant sa lahat ng terms ng sequence, yan ay magiging convergent pa rin and it will converge to k times the limit of the original sequence. Right? Tapos gagamitin ko ulit yung theorem 3.1 kasi yung theorem 3.1 ay biconditional. Nakita ko ng kahit anong sequence ng mga xn na yung k times f of xn ay nagko-converge kay KL. So ibig sabihin by theorem 3.1, yung limit ng f of x as x approaches x sub 0 ay, limit ng k times f of x ay equals sa KL. Kaparehas yung limit, kaparehas yun ang limit nung sequence of function values. And basically, that ends the proof of theorem 1. Tapos ganito rin yung mangyayari dun sa statement number 1 in this corollary. Ganito rin yung mangyayari dun sa remaining statements in the corollary. Okay? Ganito lang yung template talaga. Gamitin niyo yung assumption na limit ni f at saka limit ni g. May problema pa, may typo pa pala dito. Limit to dapat ni g ay equal kay m. Okay, pa-edit na lang guys. Yung pangalawang limit na limit ang g of x as x approaches x sub 0 ay equal kay m. So, magiging template nyo sa proof ng remaining statements ay gamitin yung theorem 3.1 dito. Okay? Meaning, i-translate yung limit ng function into the limit of any sequence of function values wherein the abscisses are approaching the limit point x sub 0. Tapos, mag-appeal kayo dun sa algebraic limit theorems para sa sequences, the analog theorem mula sa unit 2. Tapos, pag nakuha mo na yung conclusion ng algebraic limit theorem for sequences, gumamit ka uli ng theorem 3.1 para maibalik siya dun sa limit ng function. And that is that simple. 3 steps para ma-prove itong tatlong statements na to. And you can do that for any theorem na kaya nyong itali sa isang theorem na nanggaling sa unit number 2. Okay? Ayan pala, sinabi pala dito sa hint. Alright? So yung theorem 2.3, yun yung algebraic limit theorems para sa mula sa module 2 or mula sa unit 2. Alright? Now, another nice consequence of theorem 3.1 is a divergence criterion for functional limits. Ang sabi kasi ng theorem 3.1, ang limit ni f ay equal kay L if and only if, okay, pag kumuha ka ng kahit anong sequence ng mga xn's na nagko-converge kay x sub 0, ang makukuha mong limit ng mga function values ay laging magko-converge kay L. And that will work for any choice of sequence of x sub n's. Alright? So, ibig sabihin, strong yung sinasabi ng theorem 3.1. Kahit anong sequence ng mga xn's, yung corresponding sequence of function values magko-converge kay L. And that will bring forth a divergence criterion for functional limits. And it reads this way. Kapag meron ka isang function f, tapos kumuha ka ng dalawang sequences, dalawang magkaibang sequences ng mga xn's. Alright? So, meron kang sequence xn, meron kang sequence ng mga yn, alright? Tapos, nanggagaling silang parehas dun sa domain. Kapag itong dalawang sequence na to ay nagko-converge kay x sub 0, pero yung limit ng sequence of function values ay hindi equal sa isa't isa, then yung limit ng function ay hindi nag-exist. Right? Kasi sabi ng theorem 3.1, kumuha ka ng kahit anong sequence na nagko-converge kay x sub 0, tapos buuin mo yung sequence of function values, magko-converge yon dun sa limit ng function L. Alright? So, strong yon. That's for all. Ang sabi ng corollary 3.3, pwede natin gamitin yon as a divergence criterion para sa isang function. Meaning, kapag kumuha ako ng dalawang magkaibang sequence mula dun sa domain, pero parehas na sequence na yon ay nagko-converge kay x sub 0, pero pagka nagkataon na magkaiba yung limit ng mga function values nila or ng sequence ng function values nila, ibig sabihin yung limit ni f as a function will not exist. Right? Now, that directly follows from the from theorem 3.1. I don't think we need a proof for that. Pero ano lang siya, binali-bali lang yung implications ng theorem 3.1. So at this point pa lang, pwede na tayong makapag-conclude na yung limit ay hindi nag-exist even without using the epsilon delta definition. Sa math 36, para mapakita na yung limit ng isang function ay hindi equal sa isang number, ang ginagawa natin, tinatry natin ipakita na nag-hold yung negation ng definition. All right, which is very tedious to do. But corollary 3.3 gives us a nice way of checking whether a function is convergent or not. However, or if the limit of the function exists or not. Kaya lang medyo matrabaho to. Kailangan tayo magbuo ng dalawang magkaibang sequence na parehas nagko-converge kay x sub 0, pero magkaiba yung limit ng sequence ng function values. Okay? So to illustrate, tingnan natin tong example 3.4. Kailangan daw nating ipakita na yung limit ng sine 1 over x as x approaches 0 does not exist. Okay? So if you want to use corollary 3.3, then ito yung strategy. Kailangan makahanap tayo ng dalawang sequence na nagko-converge kay x sub 0. In this case, our x sub 0 is 0. So we need to invent or to create two sequences na nagko-converge kay 0. But not just that. Yung dalawang sequence na yon dapat makapagbigay sa atin ng sequence of function values na magkaiba yung limit. Okay? So pagalingan to mag-isip ng dalawang sequence. Dalawang bagay yung babantayan natin. Yung dalawang sequence na yon dapat ay mag-converge kay 0, pero dapat yung sequence of function values nila magkaiba ng limit. Okay, the handout suggests this solution. Yung unang sequence niyang kinonsider ay 1 over 2 n pi. And clearly, when n becomes very large, the denominator becomes very large. 1 divided by a very large number, that will go to 0. All right? So ibig sabihin indeed, yung sequence x sub n converges to 0. Okay. And then yung isa pang sequence na kinonsider ni handout ay yung sequence ng mga 1 over 2n pi plus pi over 2. Okay? So in the same fashion as n goes very large, 2n pi also grows very large. Pag dinagdagan ko siya ng pi over 2, lalaki pa siya ng konti, but nevertheless, the denominator will still be a very huge number. 1 divided by a very large number, that will go to 0. So indeed, yn also converges to 0. So ito na yung dalawang sequence. Meron na tayong dalawang sequence, parehas nagko-converge kay 0. Ang tanong, and this is the crux of the solution, yung sequence mga function values ay magko-converge sa magkaibang value. Right? So tingnan natin. Tingnan natin ano yung itsura ng sequence ng function values ng mga xn. Okay. So ito ay magiging sine ng ano nga yung function natin? 1 over x. So ito ay 1 over x sub n. Alright? Pero ano ba si x sub n? Si x sub n ay 1 over 2n pi. So this is 1 over, this is 1 over 2n pi. Simplify the argument, we will just have 2n pi, where n is a natural number. And we know that that the sign of any multiple of 2 pi will be equal to 0. Okay. So ibig sabihin, ang sequence ng f of xn ay puro zeros lamang. And we know this will converge to 0. Okay? So that's it. Now, at this point, we are praying na yung f of yns ay hindi mag-converge kay 0 para tapos sa tayo dun sa proof. Right? So tingnan natin. Tingnan natin yung f of yns. Ano yung itsura ng sequence ng mga f of yns? Ito ay sine ng 1 over yn. Okay? Pero yung yn ay equal kay 2n, ay equal kay 1 over 2n pi plus pi over 2. Oops. Tapos isi-simplify ko to. Yung fraction, ito na lang yung matitira. Alright? And this is sine ng 2n pi plus pi over 2. So sa unit circle, nandito lagi yung mga 2n pi. Dagdagan mo pa siya ng pi over 2, pupunta siya dito. Alright? So ibig sabihin, yung sequence ng mga f of yns ay puro sine of pi over 2 lamang yung laman. Pero ano yung sign ng pi over 2? Equal lang yung kay 1. So the sequence of f of yns ay constant sequence lang ng mga 1s. And we know that this constant sequence will converge to 1. And we are rejoicing right now kasi maganda yung nakuha natin ng dalawang sequences. Yung dalawang sequences gave birth to two sequences of function values, one that converges to 0, one converges to 1. Dahil nakakita tayo ng dalawang sequence of function values kung saan yung mga abscissas ay nagko-converge kay 0, pero yung sequence ng mga function values ay magkaiba yung limit. So by divergence criterion corollary 3.3, we can conclude that the limit of sine 1 over x does not exist. Okay? Does that make sense, guys? Kaya ba na ganito yung gawin sa homework? Ganito na lang kaya ang homework. Okay lang ba sa inyo? I'll ask you to show that the limit of a certain function does not exist. And this is one of the solutions that you can do. You can use corollary 3.3. Wala nagre-react ka. Pag-usapang homework, ayaw nyo talaga magsalita. No? Okay, maybe I can give one more example. Kailangan ko palang i-edit itong statement number 2 kasi hindi naman dinefine kung ano yung Dirichlet function. Okay? Pero sige, gawin ko yung Dirichlet function. Basically, the Dirichlet function is the characteristic function of the rational numbers. So basically, the Dirichlet function f of x is defined to be equal to 0 if, it's equal to 1 if x is a rational number, and 0 if x is an irrational number. Okay? So yan yung tinatawag natin na Dirichlet function. Pag nag-plug in ka ng isang rational number, ang output ay 1. Nag-input ka ng irrational number, ang output niya ay 0. And we want to show that the limit of the Dirichlet function as x approaches 0 does not exist. Okay, so there are various ways on how to answer this problem. So we want to show that the limit of f of x as x approaches 0 does not exist. Okay. So there are several solutions dito, pero kung gagamit tayo ng corollary 3.3, pwede tayo maghanap ng dalawang sequence na nagko-converge kay 0, pero dapat yung sequence of function values nila ay magko-converge sa dalawang magkaibang numbers. So yun yung goal natin. So I think here I can define xn to be the sequence 1 over ano kaya? Sige, 1 over n. So yung sequence 1 over n, sila ay magko-converge kay 0, obviously, right? So this is 1, 1/2, 1/3, 1/4, 1/5, 1/6, and so on. As n increases, the value tends to approach 0. Okay? So, okay, that's fine. Tapos tingnan natin, ano yung sequence ng mga function values? F of 1 over n. Well, bawat isang term dun sa sequence 1 over n ay mga rational numbers. So, ibig sabihin, pag kinuha ko yung sequence ng function values, alright, so siya ay magiging f of a rational number, and the function value of all rational numbers under the Dirichlet function ay equal kay 0. So, ito, yung sequence ng mga function values ng mga 1 over n ay sure tayo mag-approach kay 0. Okay? Do you agree, guys? Mali. Dapat hindi pala kayo nag-agree. Kasi ito ay equal kay 1. Tama ba? Yes. Dirichlet function value ng rational ay 1. So yung f of 1 over n magko-converge kay 1. So the next challenge is find another sequence that also converges to 0, but we want the sequence of corresponding function values not converge to 1. Okay? Can you guys give me a suggestion? Ano kaya yung isang sequence na pwede kong gamitin? Dapat yung sequence na yun magko-converge kay 0, pero yung sequence of function values nila ay dapat hindi mag-converge kay 1. So, sige nga. Habang nag-iisip kayo, I'll give you 1 minute to think. Medyo ubusin ko na yung kape ko. Sige nga. Anyone? Mahirap ba mag-isip? Medyo constructive kasi, no? Yung paggamit ng corollary 3.3. Kaya siguro walang sumasagot kanina sa tanong ko kung okay na yan yung homework. Parang mas madali pang mag-prove, no? Mag-direct proof kaysa mag-isip ng sequence, no? And that's usually the case. Mas nadadalian ako sa direct proof kaysa sa proof by construction. Kasi medyo kailangan creative ka sa constructive proofs. Okay, one hint. You cannot choose your sequence to contain exclusively rational numbers. Kasi kapag gumawa ka ng sequence ng mga x's na nagko-converge kay 0, tapos lahat ng mga x's na yun ay rational numbers, hindi na pwede kasi magko-converge na yun kay 1. So, kailangan yung isipin ngayon, kailangan humubuo ng sequence na dapat hindi exclusively rational numbers yung laman. Anyone? Come on guys, kaya niya. So yun na yung clue. Dapat yung sequence yung ibibigay nagko-converge kay 0 pero hindi rationals lahat ng laman. Sirit na? So sir, kung yun yung hint mo, ako na lang yung sasagot. Ayan, si Prince. Thank you, Prince. Kala ko magmo-monologue na ako dito eh. Tingnan natin kung ano yung sagot ni Prince. Habang nagta-type si Prince, baka may naisip din kayo. Pwede niyong i-share. Uh-huh, 1 over square root of n. Actually, that's the same sequence I'm thinking of, all right? So obviously, thank you, Prince, that's right. The sequence ng mga 1 over square root of n will converge to 0. Kasi kapag si n ay lumalaki, yung square root ni n ay lumalaki rin ng lumalaki. So yung denominator lumalaki ng lumalaki, yung numerator ay constant, so the quotient will go to 0. But what is the behavior of the sequence of function values? Sige nga. Bakit magwo-work yung sequence na binigay ni Prince? Ang gusto nating reason, dapat yung sequence of function values hindi dapat mag-converge kay 1. But why are we sure that this will not converge to 1? Or actually, we can say more, right? So ano yun, guys? Ano yung behavior ng sequence na to? Right. So maybe we can list down the first few elements para makita natin yung behavior at makumbinsi tayo na hindi yan magko-converge kay 1. So when n is equal to 1, we're gonna have 1 over 1. Okay, yeah, may sagot si Michael. Thank you, Michael. Since kapag ka po nag-substitute ng mga values ng n ay magiging irrational po siya. Yeah, I'll just need to quantify your statement, Michael. All right, pero I think you're on the right track. So thank you, Michael, for sharing that. Kasi magkakaroon ng mga irrationals na 1 over square root of n. And that will make the sequence of function values actually to be divergent. Magda-diverge yung sequence ng mga function values. Bakit? When n is equal to 1, so we'll have 1 over square root of 1, so that's f of 1, that's gonna be 1. Tapos kapag ka si n ay equal kay 2, kakaroon tayo ng 1 over root 2, that's irrational, so ang function value ay 0. When n is equal to 3, we'll have 1 over root 3, irrational, function value ay 0. When n is equal to 4, we will have 1 over 2, which is rational, so ang function value niya ay 1. Tapos pag n equals 5 ay so on, ay magsi-0, tapos wala tayong madideduce na pattern. Kasi nagiging rational to kapag si n ay perfect square. So there will be a bunch of ones and zeros scattered all throughout, di pala ones and zeros. There will be a few ones that will be scattered in this sequence. That makes this sequence divergent. So this is divergent. Okay. Ang kailangan ng theorem ang 3.1 ang sa corollary 3.3 pagka nakita ka ng dalawang sequence na nagko-converge kay x sub 0 pero magkaiba yung kanilang limit ng function values, then hindi na magko-converge yung function. Alright? Dito nakakuha tayo ng dalawang magkaibang sequence, parehas nagko-converge kay 0, pero when we form the sequence of function values, yung isa nagko-converge kay 1, yung isa ay divergent, then we can say that the limit of the Dirichlet function as x approaches 0 does not exist. Okay? Now, so your choice of the sequence is not unique, so you can think of other sequences. Medyo fancy pa nga yung 1 over root n ni Prince, okay? Another possible answer is say pi over n, right? Pag kinuha mo yung sequence na yan ay pi over 2, pi over 3, pi over 4, pi over 5, and so on. Mga irrationals, yung pi over n. Pag kinuha yung function value ng mga pi over n, since all of the pi over n's are irrational, then the function value will be 0. Or the sequence of function values will just be the constant sequence 0. So yung function value ng mga pi over n will converge to 0, then this could have been your second sequence. All right? So maraming posibleng sagot. So kayo na lang yung bahala mag-isip kung ano yung unang pumasok sa isip nyo that will be sufficient for you to appeal to corollary 3.3. So that's perfectly fine. Okay? So I think that ends. Di pa pala tapos yung section 3.2. Kaya ng umaga nung nagbabasa ako ng unit ng lecture notes, sabi ko kaya kong tapusin hanggang 3.3 ngayon. Mukhang hindi na naman. So 3.2 lang yung natapos natin. But yeah, let's just finish it off with a couple of definitions which pertains to one-sided limits. All right. So I think we can do this in 8 minutes. So sa definition 3.2, dinefine lang natin kung kailan siya nagiging left limit point at kailan siya nagiging right limit point. But intuitively, ang isang number x sub 0 ay isang left limit point ng set A kapag yung mga elements ni A ay nagkukumpul-kumpulan mula sa kaliwa ni x sub 0. All right? Meaning for any delta greater than 0, the left ball, paano ba natin itong tatawagin? Kasi siya ay B delta minus. Ito yung kalahati ng epsilon neighborhood o kalahati ng delta neighborhood ni x sub 0 pero yung nasa kaliwa. So let's just call this the left part ng delta neighborhood ni x sub 0. Right? So yung left part ng delta neighborhood ni x sub 0 will contain elements of A aside from x sub 0. Okay, saka siya magiging left limit point. Ganun din para maging right limit point. Ibig sabihin nagkukumpul-kumpulan yung mga elements ni A dun sa kanan ni A. Meaning for any delta greater than 0, okay, the right part or the right half of the delta neighborhood of x sub 0 will contain elements of A different from x sub 0. And then if a real number is both a left limit point and a right limit point of A, then it is a limit point. Right? Tapos, gagamitin ko tong konsepto ng pagiging left limit point at pagiging right limit point para ma-define yung one-sided limits. Yun yung ibibigay ng definition 3.3. Now, if we have a function f defined on a set A who has x sub 0 as a left limit point, then we can say that the limit of f of x as x approaches x sub 0 coming from the left ay equal kay L if and only if whenever you have an element x in the left half of the delta neighborhood of x sub 0, or actually you can say this is x sub 0 minus x is less than delta. Okay, so whenever x sub 0 minus x, it's between 0 and delta. So ibig sabihin, ito lamang yung mga x's na super lapit mula sa kaliwa ni x sub 0. Then the epsilon inequality still hold. Then we can say that L is the left-hand limit of f at x sub 0. Tapos similar din, para ma-define yung right-hand limit, okay? Papalitan lang natin ito ng plus, okay, as dapat si x sub 0 ay right limit point. Tapos isusulat natin yung limit as plus lang yung superscript. All right? Tapos this will happen if and only for all epsilon greater than 0, there exists a delta greater than 0, such that whenever a number x is in the right half of the delta neighborhood centered at x sub 0, then the epsilon inequality will hold. Ito mababaliktad lang. Instead of x sub 0 minus x, ang concern na natin ay x minus x sub 0. Kasi yung mga x's nasa kanan na ni x sub 0, so that's the only way that this will be positive. Okay? And then we will cap this off by Theorem 3.2. Sa Theorem 3.2, ang sinasabi niya, kapag ka meron kang limit point, kailangan ko palang i-fact check yung sinabi ko kanina. Sinabi ko ay, kapag ka siya ay left limit point at right limit point, then automatic siya ay, tama naman pala yung sinabi ko kanina. Pag siya ay left limit point, automatic na siya ay limit point. Kapag ka siya ay right limit point, automatic na siya ay limit point din. Kasi yung pagiging limit point, kahit galing lang sa isang direction. Pero kapag ka siya ay limit point, hindi tayo sure kung siya ay left limit point and siya ay right limit point. So hindi magpa-follow na pareha siyang left at saka right limit point porket siya ay isang limit point. Kasi pwede kang maging limit point kung left limit point ka lamang. Pwede kang maging limit point kung ikaw ay right limit point lamang. Pwede ka rin maging limit point kung parehas kang left limit point at saka right limit point. Okay? So kung meron tayong isang x sub 0 na parehas left limit point at right limit point ng isang number ng isang set A, then the limit of f as x approaches x sub 0 is equal to L if and only if the left-hand limit and the right-hand limit are both equal to L. Ito ay definition natin dati sa Math 36. All right? Pero ngayon, isa na lamang siyang theorem. And then you might be thinking, sir, hindi ba niyan i-contradict yung sinabi natin last time na ang limit ng square root of x as x approaches 0 ay equal kay 0? Because this was my contention before, right? Consistent ba yung Theorem 3.2 dun sa ating na-develop na theory? And I say yes, consistent yan. Kasi, okay, yung limit po, yung right-hand limit ni square root of x as x approaches 0, obviously equal pa rin yan kay 0. Math 3016, nothing big, right? Pero pag kinuha mo yung limit ng square root of x as x approaches 0 from the left, ito ay does not exist. Okay? Kasi wala kang dadaanan mula sa kaliwa ni 0 papunta para ma-predict yung behavior ni root x. Alright? So sir, paano kaya nire-reconcile? Sabi mo yung limit ng square root of x ay equal kay 0, pero alam ko yung limit from the right ay 0, limit from the left doesn't exist, tapos meron kang theorem 3.2 na yung limit is equal to L if and only if the left and the right hand limit are equal to the common value. All right. Now, the kicker here is in the fine details. Ano yung fine details? Nag-hold lang si theorem 3.2 kapag ka si x sub 0 ay parehas left at saka right limit point. Okay? Now, 0 is a right limit point of the domain of square root of x, but it is not a left limit point. So theorem 3.2 doesn't apply to the case of 0 with respect to the function square root of x. Kasi hindi siya parehas, kasi si 0 ay hindi parehas left limit point at saka right limit point. But the fact that 0 is not a left limit point of square root of is not a limit point of the domain of square root of x, then I don't think that is sufficient enough to discount the fact na pwede pa rin nating bigyan ng limits si square root of x. Because anyway, we don't want to talk about x's to the left of 0 because the function values there do not exist. All right? Kaya it makes sense lamang na tingnan siya mula sa kanan. So, kaya yung hindi pagkakaroon ng function value sa kaliwa ni 0 should not hinder us as what happened in Math 36 from giving a value to the limit of square root of x as x approaches 0. Because all that matters is to look at the behavior of square root of x coming from the right of 0 kasi yun lang yung merong mga function values. But unfortunately, sa Math 36, hindi ito kayang gawin. Kasi wala tayong konsepto ng left limit point at saka right limit point sa Math 36. But I hope this development of ours for calculus will make those things or will fix those things na medyo butas dun sa theory natin mula sa Math 36. All right? But it's not a big adjustment. It's just that kapag ka meron kang isang function na hindi mo matrace mula sa kaliwa, all right? Kasi sabi natin para sa limit, tumingin ka sa behavior mula sa kaliwa, behavior mula sa kanan, dapat parehas yung behavior para makonclude na nag-exist yung limit. All right? So sa Math 155, okay, sa square root of x, tumingin tayo mula sa kanan. Okay, nag-approach siya ng 0. Pero wala tayong magawa mula sa kaliwa kasi wala tayong graph na ma-observe mula sa kaliwa. And it doesn't make sense to disqualify square root of x from having a limit at 0 just because there is no graph to observe coming from the right, coming from the left of 0. Okay? And thankfully, kompleto yung theory natin ngayon at we were able to give a value to square root of x, to the limit of square root of x as x approaches 0. All right? So I think I'll end here.